Hello there, I'm Beyazıt,
And I'm Emin.
and we would like to introduce you to our EE321 Zumo robot project. Let's start. In this project, we programmed the Zumo robot to scan its surroundings and count the number of the objects in an arena. The robot uses an MZ80 infrared sensor and a reflectance sensor array to count the objects and stay within the arena boundaries. Our main objective was develop an accurate and reliable algorithm to count the objects and provide visual feedback using an LED.
For the method of test and trial of concept, what we were trying to imply with this part was that we can successfully complete this project with the objects given to us. Where we have introduced them in the last section, the objects given to us was an infrared sensor, MZ80, and a reflectance sensor that's available at the bottom of the Zumo robot. We can see from the arena that's given to us, it has black interior and white outlinings. This is used for the reflectance sensor to keep Zumo in bound of the arena. Our main goal from this project was that we should be able to count all of the objects placed randomly in the arena without any interruptions or human interaction. We can successfully do this part by the infrared sensor that's available at the top of the Zumo, which is MZ80. So we can conclude that we can successfully finish this project with the infrared sensor and the reflectance sensor at the bottom of the Zumo.
We developed a search and find algorithm to detect and count objects in the arena. By calibrating the infrared sensor, we ensured accurate detection and identification of objects, following a rule that objects must have a gap between each other. We provided that the robot rotates 360 degrees around itself in order to count objects accurately. While rotating, the robot also does the counting at the same time. We used a negative edge detection method for counting, which was effective with our algorithm. The infrared sensor detects the changes in edges, and each negative edge counts as an object. Additionally, we implemented a knocking over algorithm. After counting, the robot knocks over the counted objects. For this, we calibrated the reflectance sensor to ensure proper functioning.
Throughout this project, we have foresaw and anticipated some challenges. Over the project proposal and project progress report, we have written and explained our expected challenges, and as of now, with our algorithm and counting method being finished, we will move on with a brief explanation of the challenges and their solutions. In our first challenge and our first solution, our major challenge which was faced was the robot counting the same object multiple times. Initially, we tried using delays and time-based calculations, but these methods were ineffective with identical objects of varying sizes. To solve this, we implemented a negative edge counting method. The infrared sensor counts objects only when it detects a transition from high to low, ensuring each object is counted just once. This method was effective for both small and large objects, as it prevented multiple counts by recognizing only initial edge change, improving our counting accuracy. For our second expected challenge and our second solution, we encountered issues where objects were out of reach for the infrared sensor. To solve this, we used a mechanical switch on the sensor to calibrate its range. Turning the switch clockwise increases the sensor's reach, allowing us to detect objects at the arena's edges. Additionally, we implement our search and found algorithm. Initially, we had to wander the arena to detect objects. However, with edge counting method and proper sensor calibration, we no longer need to wander. This ensures accurate detection of all objects in the arena. For the third expected challenge and the third solution, we were facing environment detection errors. This has been solved, but however not in an orthodox way. We have two solutions for this problem, where the first solution being is using our algorithm. Since our algorithm doesn't move within the arena, we don't exactly need to use or calibrate reflectance sensors, thus we won't have any environment detection error. For our second solution, which is the more orthodox way, we carefully calibrated the reflectance sensors at the bottom of the Zumo robot before putting it into the arena by showing it first black, then white, then black, then white. After the correct calibration, we have seen that this problem solved itself, where when our knocking over algorithm was used, we didn't have any problems with environment detection. For our fourth expected challenge and the fourth solution,
we predicted that we might not be able to see the LED blink after Zumo does the counting part. However, within tests, we have seen that was not the case for our Zumo robot, where we could clearly see the LED blinking after the correct algorithm and counting method was done. Thus, this problem has solved itself. In the fifth expected challenge and the fifth solution, we were expecting to face some problems regarding how our algorithms and systems interacted with each other. However, within test runs, we have seen that this was not the case, as our algorithm and counting methods complemented each other.
After developing our algorithm and counting method, we conducted several demo runs using the suggested test cases as well as 2 additional test cases we created. We did not use the knocking over algorithm unless we specified it.
In our first demo run, we placed the Zumo robot in the middle of the arena. The robot successfully detected and counted all the objects on the first try.
In the second demo run, we again had success on the first attempt, with all objects correctly identified and counted.
For the third demo run, we placed the robot in the first quarter of the arena because the middle was obstructed. Initially, we encountered a problem due to the bad placement of objects. The error occurred because of bad initial placement, where we understood that we had placed objects in such a way that they were identical, which meant that they were behind each other with no offset. Thus, we have counted the wrong result. After adjusting the placements, the test was successful.
In the fourth demo run, we placed the robot in the middle again, and it successfully counted all the objects on the first try.
In our fifth demo run, we tested the robot's ability to avoid false triggers. Initially, the robot turned more than 360 degrees and counted incorrectly due to speed miscalculations. We have seen that in our code, we forgot to rely on the millis function value regarding our change of speed. After fixing this issue, the demo run was successful.
In the sixth demo run, we combined challenges from the first and third runs. Initially, the robot miscounted due to incorrect initial placement. We have seen that the initial placements we did on those demo runs were not proper, where we put them in front of the objects which the angle of the infrared sensor can detect. After correcting the placement, the run was successful.
In the 7th demo run, we activated the knocking over algorithm. Prior to placing the Zumo robot in the arena, we calibrated the reflectance sensor. After completing the counting process, the Zumo robot proceeded to knock over all the counted objects in the arena.
In the 8th demo run, we once again utilized the knocking over algorithm after completing the counting process. Prior to placing Zumo robot in the arena, we calibrated the reflectance sensor. The algorithm worked successfully on the first attempt.
Throughout this project, we have essentially implemented search and find algorithms and used edge detection counting methods. We achieved this with the help of the infrared sensor and reflectance sensors.
By addressing the challenges we faced, we learned the correct applications and the most efficient algorithms.